Hey folks, it's Andrew from Gemba Red, and today we're going to be taking a look at yet another power meter. This one's the VLP 2000 laser power meter. I got it off of Alibaba for about $640, including shipping, so it's a really good price. And it's connected. They had a bunch of different sensors, power meter sensors. This is the 3-watt Thermopile sensor. So the Thermopile works a little bit differently than, say, the photodiode type sensors, and it's going to give us some good options for different things that we can measure because it's got a flat response for all the wavelengths, so you don't need a correction factor for the wavelength, which is great. And then this one is a beast, and it can measure higher intensity as well, so it's really great. You know, some people are kind of getting concerned that because it's got the word laser power meter, that you can only use these things for lasers. But again, these are kind of a carryover from traditionally a lot of these meters and sensors were made for lasers. But if you understand the physics and how they're designed and how they're built, they can be used for LED technology as well. In fact, you can see some of the major brands like Thor Labs. We can go to the website. I'll show you a little screenshot. And they've rebranded. They're not calling their power meters laser power meters anymore. They're calling them optical power meters, or they're just calling them power meters. And a lot of times they'll refer to the power meter according to the type of power meter. So this one, is like I said, a Thermopile power meter or a thermal power meter. And then this one's more the photodiode type power meter. So you go by the types of the power meter, and people, you don't want to get too caught up on, it's a laser power meter, so you can only use it for lasers. But that would be really restrictive kind of mindset. There are studies that have used power meters and laser power meters for LED arrays, like this one that used a Thor Labs power sensor, and we can even open up and look at that specific sensor that they used, and it was for an LED array. Or we can look at another study that was a combination of LEDs and lasers that also use an Ophir brand power meter sensor, and that was a Thermopile type. So, and a lot of times some people have poor memories, or maybe they should be using more red light therapy for their brain, because Dr. Hamblin was asked what should people use as an alternative to solar power meters, and he told them to look for laser power meters, and as he specifically cited looking for Thermopile types. And I've been following the science, I've been following the scientists, and I've been testing out different Thermopile type power meters to find one that fits. So, if people are biased and they're just trying to use par meters just so they can pretend to be a charlatan and have the only solution, even though literally no one's used a par meter or whatever in the science, that's just an embarrassment. We got to, really evaluate. We don't want to get back into a situation where people accidentally measured with solar power meters and got the wrong thing. So that's why I'm really diligent and open-minded towards testing out different types of power meters and seeing how they correlate to the lab measurements, and see what we can do with these. So that's the jux of it. So like I said, this is a really neat setup because it can measure all the way from 11 nanometers all the way up to 19 micrometers. So a very long range into the far infrared. So like I said, we're going to be able to measure some really interesting stuff with this in the near future. So make sure you subscribe. But we're just going to do a quick test today with an LED panel and see if it gives us, again, we're looking for logical measurements that correlate to some of our other tools that we know work. And that's all we're trying to do. So the first step is, we want to understand how we're going to do this. This tool measures in watts, but it's really easy to convert watts to milliwatts. Again, you just divide by a straightforward factor. So that's an easy conversion. There's nothing to see here. And then we take off this cap that protects the sensor, and that's the sensor. It's just a very dark sensor, so that way it absorbs all the wavelengths as heat, and then it calculates the intensity or the wattage that it's absorbing. So it's a neat technology, and for these LED panels, all we do is we divide by the area of the sensor. This is standard practice, especially with lasers. They divide by the area of the laser. Since we know we're going to be hitting light against the whole area of the sensor, then we're just going to divide by the area of the sensor. And so this sensor is 2 centimeters in diameter. So that makes our area calculation really easy because we are going to do pi r squared, which r is going to be 1. So 1 squared is just 1. So really we're just dividing this number, the milliwatts, by pi, which is 3.14159. And we just, so it's very simple. So we just divide this number by pi, and that gives us our intensity, our milliwatts per centimeter squared. So it should be super simple. We've got this set up. We're going to do both red and near infrared. And with the thermopile type, it also takes a little bit while to get the measurement because it does warm up. So again, that's, there's little pros and cons, so you need to think about with different power meters. This one takes a little bit longer to warm up, but that could be a good thing because maybe if you have pulsing or if you have a lot of flicker, then because it's a slower response, it could be averaging out pulsing or flicker. So again, there's pros and cons to that concept. So it looks like we've stabilized. We've got 128 milliwatts. So again, it's just a simple conversion from watts to milliwatts, so it's 128. And so the calculation is really easy. So 128 divided by 3.14159, and we get 40.7, so maybe almost 41 milliwatts per centimeter squared. So, again, that's about 12 inches away. We got the ruler out there. And so it's about 41. So that's the number we need to remember, and we're going to cross-check it with some of our other measurement tools. So here with the Hopo color, it gives us 41. So, that's really dead on, so that's really good. And let's take a look with the Sanwa laser power meter. I just got a new one. And again, this is a photodiode type. So it's reading 31 milliwatts. And like I said, with the Sanwa is kind of a pain in the butt because now we have to take our measurements from this calibration curve. So we have to do a weighted average of these numbers, and then we have to divide by the sensor area. So, I think some people think I'm trying to bamboozle them with made up numbers, but it's just because they don't understand basic math and linear interpolations. And then just, like I said, dividing by the sensor area. It's pretty straightforward. So we're going to take 31, and then we have to multiply by 0.83. That's the calibration factor for the wavelengths. And then we divide by 0.636, and that gets us 40. Again, it was all based on interpolating the calibration curve and then dividing by the area of the sensor. So just basic math here, So, but again, we get 40. So again, we're right in the range. We're dead on with these laser power meters. Again, this one's limited in its range. It can't measure much higher intensities. And so that's why I'm going to be switching over to maybe the Thermopile type for higher intensity measurements. So again, you have to understand the limitations and what's realistic with a cheap photodiode power meter that's limited in what its range is. So again, there's not just one solution that fits everything. So that's the kind of thing a charlatan would say, oh, we've got one solution that fits everything. I'm trying to be more open-minded and try different types of power meter measurements and see what we can learn from different things. And now that we've validated this laser power meter, the Thermopile type, we're going to be able to do a lot of interesting measurements. Like I said, we're going to be able to measure longer wavelengths and combinations of wavelengths and higher intensity products as well. So make sure you tune in for more measurements with this. It's going to really help us measure some more things that people have had questions about in the future. So thanks for tuning in. Hopefully this helped. We'll see you next time.